everybody. I'm at the KISS and XDEEP booth with Patrick Widmann, who is responsible for the new Sidewinder 2.0, and he is going to walk us through what's new on this rebreather. So, take it away, Patrick.
Let's do it. So, there's a couple of things. Obviously, we see that the entire design of it is very, very different. And we also want to highlight that the configuration is possible not only to be used in side mount, as we have so far known it, but you can also strap it to a single cylinder with the help of a backplate that we use as an adapter to mount it to a backplate and wing system. So, for example, if you would usually use it in side mount for cave diving, but then you're going to do a dive off a boat or maybe offshore, then you can easily just strap it to a single tank and use it like that. Now, when we look at the detail, the first question we often get is, why are the canisters suddenly square? Now, the main reason for this is that the gas flow is different. It is still an axial canister, but we changed the axis. In a Sidewinder 1 or in the Spirit, the gas flow direction was in this direction, but for us, it goes in this direction. So it is still an axial design. However, it has all the attributes of a radial absorbent, which means very short bed length, right? The absorbent bed is short, which means it is very much easier to breathe through it, right? The shorter the bed, the easier to breathe through it. On the other hand, besides the short bed, we have a very, very large surface area. What does that mean? Large surface area means that the gas can only traverse through the absorbent rather slow. That gives you a lot of time that the gas will reside with the absorbent material and therefore a higher likelihood of getting scrubbed from CO2. This allowed us two things. This change of design, first of all, gave us a possibility to add about 30% of absorbent materials, almost 8 pounds of absorbent material. And in CE certification standards, which is 120 feet, 40 liters per minute respiratory minute volume, 39 degrees Fahrenheit, so very, very, very cold, and 1.6 liters of CO2 per minute, which is incredibly a lot. We managed to do 4 hours and 20 minutes of duration, which most rebreathers can do 3 hours. Of course, because we have more soft flow line, more absorbent material, but also because we use it very, very efficiently. So what is quite interesting is although we have 30% more absorbent material, the work of breathing according to the Anstey machine is almost half, right? So it is a very, very efficient way of using this. So how are we going to fill the canister? So you see, this is basically our breathing channel, and we don't want absorbent material to fall into it. So we're gonna block the breathing channel, fill the sorb, tap, 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 fill the sorb, tap, 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 fill the sorb. Then we're gonna open it so the breathing channel is open, and we're going to put the plunger on top of it, right? And the spring has the same job than before. If during transportation it vibrates and the absorbent material settles even more, the spring is going to take up that slack and make sure there's no absorbent material falling around inside the rebreather. Now, you can see that before, cold temperature was definitely a problem. So we solved that because obviously no material will insulate better than gas. So we have a gas channel here and obviously the gas channel on the other side. But what you can't really see here, you see it rather, this is quite thick walls because there's actually a gas space in between, and this gas space is ventilated through a hole down here. So we basically have all 4 sides being insulated by a gas pocket, which gave us this really massive good performance in very cold water. Now that we have it put together, we can see that there is a Bionet system. So to mount it on our single tank is unbelievable fast and easy. Just rotate it up and we pull this bungee over. And you see this is a really sturdy platform. So you could even consider to fill the absorbent material while the canister is mounted to your tank. Another thing that is really unique to our new design is, even though we still use Molex connectors, but the connection between the oxygen cell and the circuit board inside is actually waterproof, because you can see there's a silicone gasket here. So that means that the connection between cell and circuit board is completely waterproof. And the first question usually we get is, but how do you equalize the pressure between the front of the cell and the back of the cell? And you can see those holes in here. So on the other side of this, there's a Gore vent. The Gore material is permeable by gas, but impermeable by water. So it means gas can go through to equalize the pressure between the two sides, but it makes it still waterproof. So that means if you would accidentally remove the mouthpiece without closing it, and you flood your rebreather and the water becomes caustic, and you have caustic water all over your cells, you can literally take the cell head and rinse it in fresh water, pull it out, dry it, and it works again. So this is, from the longevity for your cells and just usability, a really, really awesome feature. Something that I really like about the rebreather design also is it needs zero physical strength. So in a moment I push the head down, I can literally just, use one finger to tighten the locking mechanism, and my rebreather is ready to dive basically. We're gonna stay still on this head, or actually if you come around here, you see there's two valves. There's a valve here and there's a valve here. And they both look very similar. They're also similar in their design. They are double sealed. You have a one-way valve in it, which is basically the mushroom valve of a second stage, right? On top of it, you have a dump valve, the same dump valve that you find in a BCD. The only difference is that the gasket is not made out of rubber, which is really hard. That means if there would be like sand in the water or percolation in a cave, the rubber often doesn't seal very well. But we actually use a very soft silicone. So that means that even if there's like a bit of sand or dirt, the silicone kind of like absorbs it and it still seals very, very good. The difference between the two valves is that one is upstream in design and the other is downstream in design. So this one is upstream, which means there's a spring that pushes the gasket up. That means the only way to open this valve is by actually pressing onto it mechanically. We do this with our triceps. We use this valve in two different scenarios. First scenario is I am open circuit, right? I bailed out and I want to abort the dive. As I'm ascending, of course, the gas will expand inside my rebreather. And in order to vent it, I'm just gonna press with my triceps on top of that valve, and I'm gonna let the gas, as it expands, come out of the rebreather, and I'm not getting too buoyant. It will also allow me to flush the rebreather with breathable gas while being open circuit. So imagine you have a problem with your rebreather that forces you to go open circuit. But while you're open circuit, you manage to fix the problem, and you wanna return to your rebreather, but you wanna return to breathable gas. You can do that by simply pressing onto the valve with your triceps and rolling your right shoulder down. Gas will come out through the valve that you opened, and the gas that comes out is going to create an underpressure inside the rebreather that's going to pull the ADV membrane in, trigger the ADV, and now the rebreather starts flushing itself, right? This is a really easy maneuver because the amount of gas that goes in is directly proportional to the amount of gas that goes out. So even a novice that has never tried can do this very, very easily without losing buoyancy. Good?
Cool. Now tell me about the other valve. What?
Now on this side, actually let me move here.
Yeah, we'll go over here.
Now on this side, you see it's the same type of valve, but here the spring is on the outside pushing in. Right, so this is an actual overpressurization valve. So if there's overpressure in a rebreather, my left valve that is upstream would close, and my valve on the right hand side, that would actually open because it's downstream. So we use this to purge water from the rebreather. Imagine we come back to that scenario where I accidentally removed the DSV from my mouth, realized it was open, I put it back. I can now shake the water through the corrugated hose into my right head. I have to bring this valve to the lowest possible point, right? I'm basically putting my right shoulder down, and then I'm just pressing on the MAV button, and I'm starting to overpressurize my rebreather. At some point then, I'm gonna exhale completely, because I'm gonna keep my lungs as small as possible so I'm not losing buoyancy too much. And I wanna also like push the gas out through the OPV. At some point you're gonna hear because the water has left the rebreather and now gas pushes through the OPV and you can hear the OPV opening. In that moment you just have to raise your head and let the rest of the gas vent through your lip, and you can maintain buoyancy. Is it crazy easy? No. But I did this maneuver in front of Ed Sorensen filming in about 10 foot of water, and I did not hit the surface. I was pretty pleased with that. Do I think it is unbelievably easy to do? No, but it's definitely feasible, right? And last but not least, another change that you can see is The ADV is an actual standard second stage, and that means it's adjustable. So if you come on this side, you can see there's an opening where you can adjust the cracking pressure of the second stage via an via an Allen key. So you can choose if you want the ADV rather to be hard triggered or soft triggered. And in a nutshell, this is about it. So there's still quite a lot of plans for the future. We have a new style of MAV that is ergonomic, that has a button for thumb and index finger. There's also the plan to have eCCR upgrade version, which means there's going to be an additional box that you can add with a solenoid in it. So our plan is to just keep on building a very modular system that can be used in very different styles of configuration for different applications, but also in different styles of eCCR, MCCR, and things like that.
Wild. Tell me about the counterlung built into the wing.
Good.
Are we allowed to talk about that? Is that top secret?
Maybe not top secret, but it's one of the one of the prototypes we're building at the moment. So basically, if you imagine in the side mount configuration, we basically have a canister on the left and on the right hand side. And historically, we had the counterlung underneath the buoyancy compensator. But we also have a prototype where we have holes actually in the Cordura shell with a new design of buoyancy compensator that still accommodates space for the counterlung inside. And you basically just have the flanges sticking out here, and you can mount your canister straight onto your side mount equipment and have a pretty streamlined and neat side mount rebreather.
That is cool. Thank you very much for the introduction. I'm excited.
My pleasure.
When do I get mine? When do these babies ship?
Tomorrow. No, I'm joking. It's going to take us for the general market about until June, July next year.
We got to wait a while. All right. Well, awesome. Thank you, sir.
Hey everyone, thanks for watching our latest episode all the way to the end. You're crazy if you don't subscribe. Hit that subscribe button now so you won't miss our next episode.